All right, so we're going to be looking at the non-commutativity that exists before the probability from the amplitude squared in the normal wave function of quantum physics. So I found this in a PhD thesis that the Planck's constant is the minimum element of non-commutativity when you switch between the position and the momentum. And this is better explained by Professor Hiley in his recent paper, where he says the difficulty that occurs in all of approaches to quantum theory, it arises because in the Schrodinger picture we had the replacement of the measurement of position, but when we switch to momentum, we have the imaginary number with Planck's constant. So clearly xp will differ from px by a factor of h bar squared, which would be Planck's constant divided by 2 pi. So you have that negative frequency due to the 2 pi as with the imaginary number in the phase, with the momentum directly proportional to the frequency as a frequency difference. So the normally you would think of it in Fourier analysis as a differential, but Basil Hiley in an earlier paper, he says by emphasizing the constancy of h bar, which again is Planck's constant divided by 2 pi, and the relation of the change of position to the change of momentum approximates h bar, one tends to be led to the notion that the disturbance is dependent only on the size of the cell in the phase space. In this way, the overall experimental conditions were tacitly dismissed as irrelevant. So this is Basil J. Hiley in 1971. So again, the key issue here is the h bar is the reduced constant of Planck's constant based on the dividing h bar by 2 pi, where you're trying to maintain this symmetry of the phase space. And so his big point is that I quote in my I quote here is that I quote his same paper here. It's only when we go to Planck's constant squared and above that the Baker bracket does not reduce to the usual commutative product. Generally, terms of h or Planck squared are assumed to be negligible and therefore not discussed, but the bracket plays an important role when energy is involved. A careful study of Pauli's application of the algebraic approach shows how a Jordan product enters into the calculation, which is the same as the Baker bracket. As we have already discussed, one of the advantages of the Moyal approach is that it contains classical physics as a limiting case, as is clearly seen from the equation. There is no need to look for a one-to-one correspondence between the commutator brackets and the Poisson brackets, a process which fails. Furthermore, it is not necessary to introduce the notion of decoherence as a fundamental process in order to obtain the classical limit. This does not mean blah, blah, blah. So then it has to be used to argue against the whole approach, because the psi wave of position, momentum, and time will always be negative somewhere in phase space when quantum effects show up. Moreover, this has generated much debate, even Feynman feeling it necessary to defend the use of Wigner functions, which may be negative, But we should not even be assuming that the argument, because the position, momentum, time is not a classical observable. It is an average over a region of phase space. Note, there is no reason why a density matrix should stay positive. The positivity condition is only desirable if the psi wave of position, momentum, time is to be regarded as a probability density. So this is before any kind of collapse of the wave function. And then you have, I quote him again, what Bohm and de Broglie called this term the quantum potential energy. This new quality of energy enters as the coefficient of Planck Squared, and this is why Dirac missed the equation. Its appearance is intimately connected with the Baker bracket or Jordan product, and therefore the non-commutativity of position and momentum. This means that in the quantum domain, a new quality of energy appears, namely the quantum potential energy. We should not be surprised that a new quality of energy is involved, because the quantum vacuum is a sea of virtual particles and antiparticles. Blah, 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 blah. Thus we see mathematically the quantum potential arises as a consequence of the difference between the mean of the square of the momentum and the mean momentum squared. All this implies that the dispersion in the momentum for a single particle in quantum mechanics will in general be non-zero. For the single particle in classical physics, the momentum is always dispersion-free. In this way, we see that the star product contains the structure that guarantees the existence of the uncertainty principle, contrary to what Dirac claims. So Dirac was trying to maintain the symmetry by ignoring the underlying non-commutativity dynamic. And so this brings us back to Planck's constant. And so, again, we have the Planck's constant as a difference between the spectral terms from the Ritz-Rydberg combination principle being non-commutative. And so what Planck did was he converted the Planck's constant into a Joule's density for energy, and by doing that he canceled out the non-commutative time, and using seconds, assuming the seconds as a symmetric spatial measurement. So he could just have the frequency. And then when they convert the frequency, all of a sudden they have this ordering problem, because you inherently have the negative frequency. So this when we use the non-commutative Planck constant, then we get a distortion of the Poisson bracket. So this is another paper that I'm citing, and so the thing is that this is what in my earlier video that I posted. Oh, right here I have math professor Luke Hoffman. Then in his reply to me, I had written him about the Pythagorean theorem being non-commutative, and he's like, yeah, if we consider that the original proof is actually an oscillation between the two magnitudes, then in a sense it's like the oscillation that creates the square root of -1. Now, what he then says is that in the paper he refers to, the non-commutative Pythagorean theorem, it relies on this imaginary phase of time where the operator is a square zero called the Nilpotent operator. So when you have that Nilpotent operator equals 0, then you actually end up with the Pythagorean theorem. So in other words, that again, you have that non-commutative time inherent to the Pythagorean theorem. And that's ignored in when you learn the typical Pythagorean theorem. And so what I realized when I learned the Pythagorean theorem, it's actually derived from 9/8 cubed as the first approximation, which would be the tritone music interval. Now, the problem is that the 9/8 itself is derived from the perfect fifth as 3/2 squared to 9/4, and then halved back into the same octave. And when you square the perfect fourth, what you're doing is you're covering up that the perfect fourth is also 2/3 and not just 3/2. And therefore the perfect fifth is 3/2 is also 2/3. And so is C to F undertone, where 3/2 is C to G overtone. And so when you're just squaring the perfect fifth, you're hiding this inherent non-commutativity that then creates the 9/8. And in fact, in order to create that symmetric irrational magnitude, Philaeus had to hide the fact that you have a different fundamental tone for the perfect fourth as 4/3 when you're doubling the 2/3 as the undertone. And so that's that non-commutative dynamic that's hidden. And then Archytas said the octave as 2 is equal to the geometric mean squared. And so think about this. We're having the geometric mean squared, which in fact is actually the same issue here of the quantum potential arises as a consequence of the difference between the mean of the square and the mean squared. So you have the frequency is the octave that's squared as the geometric mean squared. So in other words, we've literally directly re-encountered the same origin of the non-commutativity, but in quantum physics, it's hidden with the same problem as the difference between the geometric mean squared, which in this case is the mean momentum squared. And so, which Archytas's original equation was the arithmetic mean times the harmonic mean equals the geometric mean squared as the octave. And that the harmonic mean was the perfect fourth, but it actually is derived from the 2/3 that's doubled. And so it's covering up the non-commutativity that's non-local. So if we go back to Professor Hiley's paper, what we can do is we can search, we will now search Nilpotent. It doesn't come up there because I haven't loaded it. But let's see if I can find it. But he talks about the Nilpotent. I gotta find it. Okay, so here it is right here, the idempotent element. So we had it right here from math professor Luke Kaufman that the square zero is the nilpotent operator with the squared zero. So that nilpotent is actually an idempotent element. So you have this same square zero, and so this is the special role of the vacuum state, that by choosing the vacuum state correctly, we find the ordering problem disappears. So what we're dealing with is this negative frequency as a vacuum state with all matter originating from photons. And so it's based on frequency, and that brings us back to Planck's constant again. And that's why you have to use the Weyl ordering, which the energy in the vacuum state is the Planck's constant times the frequency divided by 2, or h bar. So we can see here that this frequency difference we're basically confronting the same original problem that happened at the origin of Western science, based on the frequency difference being non-commutative and actually being this vacuum energy. And so, as I quoted Professor Hiley, at higher energies, these virtual particles emerge as real particle-antiparticle pairs. So we're seeing the conversion of the virtual photons back into actual real particles, real photons. And then that gets us into the negative entropy. And it seems eminently sensible to take the possibility of a new quality of energy seriously in the quantum domain. Okay, so there's this literally a new quality of energy that has been discovered, and this is not even recognized in mainstream physics. It's not talked about. I mean, you will find mention of this whenever they bring up Bohmian physics, but then they try to dismiss it as a hidden variable, nonsense, a deterministic hidden variable, when Basil J. Hiley's pointing out that's not true at all. And so when you have this Planck's constant, he actually hid, by Planck's constant conversion to density, he also hid this negative frequency that's inherent to it. And so Basil J. Hiley's big point, again, is like, you can have the negative frequency as long as it's not probability. It's hidden in the density. And this is what Planck also hid when he converted the Planck's constant to joules. So the average, if you think of Planck's constant as the average energy of light, so it can remain hidden, except that when you have to square Planck's constant, then all of a sudden you realize that there's this hidden non-local quality of energy from the future, as due to the negative frequency and time reversed energy. It's actually a hidden quality of energy. So you can call it a force or whatever you want to call it. And so his whole point is it's not a classical observable. So this is what Alon Kahn's point also was, is that the experience of linear time as the passing of time is due to our limitation of the classical observables that are the position and momentum on the quantum level that take into account the experimental conditions. So one